Okay, I'm going to talk about Chapter 2, Boolean Algebra and Logic Gates. Okay. So basic motivation behind Boolean algebra, we want to minimize the number of gates in a logic design. So for logic minimization, right? Of course, if you minimize the number of gates in a circuit, you can actually decrease its cost, okay? So that's the basic motivation behind this. Okay, so section 2.2, basic definitions. So we're looking at Boolean algebra like other deductive mathematical systems. There's three things that will define it. It's the set of elements, in our case, just 0 and 1. Set of operators, you're going to see that. It's going to be the and, or, and not. And some postulates or assumptions, okay? All right. So this is where we're going to start. So those three things. And the author goes through and talks about these in general and gives you kind of a general idea. And I'll give you kind of an overview of that, and then we'll start to get into actually apply it with certain examples. So some basic definitions, and here you are. So mathematically, you can show it like this. It's like a set of elements, x belongs to S, and then this one here says like y doesn't belong to S, a set of elements. Set of operators, and like this is like the AND operator that we're going to use in Boolean algebra. Okay, and this just means it belongs to like set S, and then some axioms or postulates that go with it, and we'll take a look at some of those. Okay, closure, just in terms of like these are just the definitions associated with these different postulates. So is it closed? A set is said to be closed if for some set Okay, so talking about these postulates and the definitions of each of these. Okay, so a set in this case defined as S is closed with respect to a binary operator if the binary operator specifies a rule for every pair of elements. The binary operator specifies a rule obtaining a unique element in S. Okay, and this one is that for like let's say a set of natural numbers, it's closed with respect to the addition operator, and this is like just an example, for any a and b that belongs to n, so two values that belong to n, such that you'll have a third value will also belong to n. Okay, and what we find is that for addition, it is closed, but for subtraction, it is not, because you now have a number that's not part of this original set. Okay. Now looking at just like in general, let's say this operator asterisk operator, it's said to be associative if you can group, basically have different groupings of the different variables with that binary operator, and you get the same result, right? Okay. The commutative law. So this one is that the ordering doesn't matter, right? And any binary operator. Okay. So this is just some general concepts, right? We're not really talking about specific binary operators in this case just yet. Okay. A set is said to have an identity element with respect to some binary operator or operation if there exists this identity element that belongs to S, belongs to that set. And it has the property where you have some operation or perform some operation with some operator where that in this case it's commutative, where that you perform that operation and you have the end result is essentially the same as the value by itself without that. Okay, so it could be like 1 times x, let's say, it gives you x, but in general we'll see if we can do this to have an identity element for different operators. So if we look at it from the perspective of the element 0, in some set. So let's say if you had a set of integers, and this is just an example, because this for this particular case, that um, there's an identity element. Zero is an identity element for the addition operation. Okay. Uh, the set of natural numbers does not, since x is not included in the set, right? But for this case, integers does. Okay, so the inverse basically says, you can, if you do some operation or some operator, you perform an operation with that operator, that you can result in an identity element. So like for example, for the set of integers, you could say that for this operator, you have, when we're dealing with its inverse, in this case, add addition, right? So if you do an addition, that addition with its inverse, in this case, you come up with it's equal to 0. So here's 1, okay? Okay. And the key point here is that they both belong to that set. So for integers, you do have like whatever value, whatever integer. You also have its negative. So then this comes out to be true, which means essentially has inverse. All right. And the last one is distributive law. Okay. And basically follows the rule how you can distribute it out. Okay. So this one's basically just saying like this x asterisk y dot x asterisk z, right? So how it distributes out. So it'd be like if it could be addition or multiplication, or however. In this case it says it's distributed over the dot operator. So same thing is that in this case it's these are just two operators, two generic operators. Okay, and the key point is like it's distributed over the dot here. So the main thing is this is a basic assumption for us to deduce the rules. All right. So, if you understand this in general, that's good. So as we take the next step and see how it applies to Boolean algebra. So this idea of a field, and it's basically it's a set and the two binary operations of addition and multiplication. Both are commutative, associative, contain identity elements, and contain inverse elements. Basically, this is a summary of the previous rules that we just looked at, 1 through 6. Okay. Binary operators used for addition. The plus sign is used for addition. The additive identity is 0. Well, we know the multiplication identity is going to be 1. Additive inverse is just subtraction. The binary operator defines multiplication. And then if it doesn't belong, and for special cases for a not equal to 0, the multiplication inverse is just 1 over a. Okay. And then the only distributive law that applicable that of dot is over addition. Okay, so this is the only one where it works. Okay, for when we have the two operators, addition and multiplication. Okay, so now we start getting into specifics of Boolean algebra. Okay, section 2.3, axiomatic definition of Boolean algebra. Okay, so the elements of Boolean domain are 1 and 0 by convention, and the basic operations of Boolean algebra are conjunction, disjunction, and negation. Right? And in Boolean algebra, we basically represent this conjunction with an and, disjunction is the or, and negation is the not. Okay, so those are our 3 Boolean operators. Okay, and we can go through those same 6 postulates on how it applies to Boolean algebra. So it's closed with respect to the or, and this is the and operation essentially. This is the or. Yeah, addition is the or operation. This is the and operation. Okay. So it's closed with respect to these operations, which just basically means, we have two elements, 0 and 1. So the result of these operations will be a 0 or 1. Okay. And then the identity elements with respect to the OR operator. And so it's x OR 0 equals 0 or x, which is just equal to x. Okay. And the element 1 is the identity element with respect to the AND operation, right? And it's commutative with respect to OR, and it's also commutative with respect to our AND operation. All right, and it's also distributed over OR and distributed over. I'm sorry, the AND this is the AND operation. Oh, sorry. So the AND operator is distributed over OR, and the OR operation is distributed over the AND. Okay, and this gives you an idea of how you can break it up. So it works both ways. All right, and for the and so for every element x that belongs to B, there exists a complement element, okay, such that x or not x equals 1 and x and not x equals 0. So what does this basically means? 0 or 1 equals 1, 1 or 0 equals 1, and this is the same thing as 1 and 0 equals 0, 0 and 1 equals 0. Okay. And the last one just says there's at least two elements that belong to it, such that x is not equal to y, right? In our case, you know, you could have a 0 if not equal to y, and if this is 0, it's not equal to 1, and 1 is not equal to 0. Another thing that's commonly used is a truth table. And the truth table is used to define essentially, all the combinations that can occur for each input. So if you have two variables or two inputs, you'll see like two inputs to a gate. This basically defines the output. So x and y are inputs, and this is basically our AND operation or AND operator. And this is the result you would get, right? So these are all the possibilities. These two are zeros, 0, 1, 1, 0, 1, 1. And if you AND them together, here's your output. If you OR them together, what you recognize here is that the only time it's not a 1 is when they're both zeros. Okay? And then the last one is just the inverse. So if x is 0, x naught is 1. If x is 1, x naught is 0. Okay? The next one just demonstrates the validity of these. Okay? And it says basically it's closed with respect to the two operators, the not and the or. Okay. So what we'll find is the result is either a 1 or 0. That's all we can have. So it's closed with respect to those two operators. Okay. And then also from our tables, we can see that the identity elements for those, which is just postulate 2, what we previously saw. And just from the binary operator tables, we can see that it's commutative also. Okay, so it doesn't matter the order. And the distributive laws, and how you can show that is true is you just come up, let's say here's our three inputs, x, y, and z. Here's all the possibilities for that. So there should be 8 different possible inputs. And if you OR them together, you can see what the result is if you do y or z. And then if you do whatever the result is here, and then you do an AND with x, right? So these are like your three inputs, and then you do an AND with x. What you'll see is that the only time this is going to be a 1 is if, this one, the result of this is a 1, and this is a 1. So what you'll see is when you go through here is that x or, for example, x or z is a 1, but x is a 0. I'm sorry, y or z is a 1, and x is a 0. You're going to see it to be a 0. The only ones you're really going to look at is when x is a 1. So these last 4, right? And what we'll see is that if we look at y or z, we have to have both 1s. So we're looking kind of here is a 1, but this is a 0, so our result is 0. And in this case, these are all 1s, these are all 1s, so then we're going to have a 1. Okay? And then just taking that, one step further, doing the not not operators separately. So if you did them separately, like uh, x dot y, which is x and y, and then doing x and z sort of separately, and then you're going to add the two together, you can verify that yes, this really is true. It's the same as if you had done just this. And what we notice is that this column and this column are the same. Okay, so that's just showing that that's true. All right, and you could do the same thing. Okay, you could do it with the OR operator. The law, the distributed law of the OR over the AND can be shown also by doing the same thing as this. And you could do the same thing with complements, right? And it's easy to see this if you just go like, you could look at any of these, like where when x is 0 and y is a 1, essentially is this, right? So anytime these are different, x and y are different, right? So they're different here. So these inner four are all different, and we should expect that, you know, the output of, oh, this is y or z. But if you just do the OR of these, you'll recognize that, yeah, this is true, right? Okay, easily to show that. I was going to show you this, but of course it's with z. So we should look at z, right? When y and z are different, right? So y is 1, 0, 0, 0. So we can look at these, right? And what we notice, of course, these are 1s, and these two, when they're different, these are both 1s, okay? So it's easy to show this, okay? And number 6, just basically, we only have 2 elements, right? And you could have y is not equal to 0. Well, 1 is not equal to 0, of course, right? So this could be shown very easily. All right, so this is really our foundation for this. Okay, so then it's just a matter of applying applying those 6 postulates to come up with our theorems and properties for Boolean algebra. So one of the principles that's going to be important for us is this idea of duality principle. And what you're going to find in this case is that there's going to be, you know, the basic idea behind it is going to be different ways where we can, you know, essentially represent the same Boolean expression, okay? And with this duality principle, what we're going to find with algebraic expression, all we have to do is we can change the AND or the OR operators, the OR and the AND operators, and replace all the 1s with 0s and all the 0s with 1s, and we can come up with essentially an identical way of representing the same expression, okay? And we'll see that. Okay, postulates and theorems. And basic ideas, postulates are assumed to be true, and theorems have to be proven to be true, okay? And what we'll do is, you know, the next slide here, this goes through the theorems, the next couple of slides. What I want to do is I'll just go through one of them and talk a little bit about the others and show you the process here, how you can show that it's true, okay? So we'll look at theorem 1a to start with, which is right here, theorem 1a, okay? Okay, so the statement here just says, you know, x or x is equal to parens x or x, and then ANDed with 1, and this is from postulate 2b, okay? Now, that's right here, okay? What you can recognize here is that you can replace, you know, anytime you see these variables, that actually could be an expression, okay? And you can just substitute in for that expression, all right? So going back to here, just as x or x is equal to that, using that postulate, which is basically saying, you know, whatever expression dotted with 1 or ANDed with 1 is just that, whatever that expression or that variable is. The next step, in this case, you just use 5a, okay, which just says x or x naught equals 1. So you just substitute in for 1 with x or x naught. Okay, so the next one, you'll see we use postulate 4b, okay? It's x or x ANDed with x naught, okay? So this is just an AND operation, all right? So in this case, if you look at it, you'll see that you could substitute in for x, substitute in for y with x, okay, right here. And then the second part is substitute in for z with x naught right here, okay. Then as a result, the x and the x naught just show up here, x and x naught, which is just the y and the z as shown um, right here, the y and the z, okay. So the next step, you can see x ended with basically its complement or inverse. That's going to be 0. So x or 0, of course, is just going to be x, which is shown in postulate 2, right? X or with it 0, it's just going to be x. And that's all this is. Okay? So you can follow the same process with the others to show that they're true. And, you know, it's good to take a look at this and see how these are evaluated and how they're used to come up with these results. Okay, so in the end, this is the result, right? Because this is what we're going to do when we start to, simplify the Boolean expressions using these theorems and postulates. Okay, and there's another page of this. You can continue on this. Um, and this, in this case, a little bit different, like 6b. What you'll notice in this case is that they use the truth tables to determine that. Okay. And if you look at the end result here, you'll see that this is true, right? So this is just saying, um, coming up using the appropriate postulates and theorems, you can simplify this to essentially to this, right? Okay. And then you'll find the result is it's just x, right? So whatever x is, right, 0, 0, 1, 1, is the same as this, x or x ended with y. Okay. All right. So you can go through this process to take a look at this. Okay. But it's the same, similar idea. It's like, what's the end result? What we're trying to show is that for all the combination of inputs, you get the same result, right? Okay. As some other expression, then essentially they are identical. All right. So if the truth tables match, they match, right? The expressions are identical. Okay. So for this one, operator precedence. Okay. This is an important one. We need to know how to evaluate these, right? So when we go and evaluate an expression, so this will be important when you go and evaluate the expressions. Parentheses has the highest precedence, then the not, which is like a unitary operator, only operates on one variable or operand, and then the and then the or. Okay,